extra minutes.
All right. So we are working towards being able to sketch different functions using calculus, using derivatives. So one thing that we can use derivatives for is to determine whether a function is increasing or decreasing. Is the graph rising as you go left to right or falling as you go left to right? So in the case of that graph, from segment A to B and from C to D, the graph is decreasing. It's a decreasing function. Whereas from B to C, it is an increasing function. So we're going to see that we can use derivatives to determine where a graph is increasing or decreasing. So if a function is increasing over an interval, then the slopes of the tangent in that interval will be a positive value, which means a derivative will be positive. And if a function is decreasing over an interval, the slopes of the tangent in that interval will be negative. So that means the derivative will be negative, because remember, the derivative gives you the slope of the tangent line. So in this case, we're not going to determine what the actual slope is. We're going to determine whether the value of the derivative is positive or negative. So this question says, find the intervals of increase / decrease for the following functions. So the first one is a quadratic. It's a quadratic that opens upwards. So as you go left to right, from negative infinity to where the vertex is, the function will be decreasing. And then after the vertex, it will be increasing. So we can use derivatives to find out where, in this case, the vertex is. Because remember, and if we look back at the graph on the previous page, at point B, the graph changes from decreasing to increasing. And what's important about point B, it's the minimum value of the graph. If you're at a minimum value, the tangent line will be horizontal, which means its slope is 0, which means the derivative is 0. And at point C, the same thing will happen. That's the local maximum point of that graph. So at that point, at point C, the tangent line will be again horizontal. It'll have a slope of 0, which means the derivative will be 0 at that point. So that's how we're going to start these. We're going to find out where is the derivative of 0. That'll tell us where we have a local maximum or local minimum point. And in the case of the first one, there'll only be one place where that happens, because it's a quadratic. A quadratic that opens upwards, so there will be a vertex, and that will be a minimum point of this graph. To the left of that, the function will be decreasing. To the right of that, it will be increasing. And we know that because what we know about quadratic functions. But when we get to question 2, where it's degree 3 or higher, then we don't automatically know if that first point is going to be a local max or a local minimum. Okay, so we're going to use derivatives to find all that out. But for question 1, again, we start by finding the derivative, which will be 8x minus 5. And again, the vertex, in this case, the vertex will be where the derivative is 0. So we let the derivative equal 0. So 8x will equal 5, and x will equal 5/8, or 0.625. Now, as we said, we know that because this is a quadratic that opens upwards, that this point where x is 5/8, that's where the vertex is. That'll be a minimum point. So the graph would have to be decreasing to the left of that and then increasing after. However, we can also show that by starting with a number line, putting our 0 of the derivative of 5/8 in the middle of that number line, and then checking back using the equation of the derivative, find out what we get on either side of this value of 5/8. So 5/8 is 0.625. A value to the left of that would be 0. And when x equals 0 here, you're going to get 0 take away 5, which is negative 5. So the fact that the derivative is negative in that interval tells us that the function is decreasing. We already knew that because of what we know about quadratics. but this just confirms that using derivatives. And if we choose a number to the right of 5/8 or 0.625, a value like positive 1 in the derivative, 8 times 1 is 8, take away 5 is a positive 3. That confirms that the function is increasing in that interval. So again, we're asked to state the intervals of increase and decreasing. This graph is increasing from 5/8 to positive infinity. And note we use the rounded brackets here because at 5/8 the graph is neither increasing nor decreasing. That's where the vertex is. And the function is decreasing from negative infinity to positive 5/8. All right, so there's that first one. Now, for question 2, it's a third degree polynomial. We're going to find the derivative, which we can then use to find out where those local max and min points are. The derivative will be 3x squared, 3x squared plus 12x plus 9. And again, we want to find the zeros of the derivative. That's where we'll have a local max or min. There's a common factor of 3 there. We're going to solve this by factoring it. That's usually the easiest way to solve a quadratic. And then that quadratic that we're left with after the common factor can be factored to x plus 3, x plus 1. So our zeros of the quadratic are at negative 3 and negative 1. So like we did in the previous one, we'll set up our number line. And in this case, we're going to have 3 intervals to look at. Everything to the left of negative 3, what happens between negative 3 and negative 1, and what happens after negative 1. So again, we're going to choose a number in each interval and plug it into the derivative to find out whether it's positive or negative. If we use a number like negative 4, I'm going to use the factored form for this. When x is negative 4, the first factor is positive 3, and we don't really care about what the value is, just whether it's positive or negative. The second factor, again, I'm using a number like negative 4. Negative 4 plus 3 is negative 1, and negative 4 plus 1 is negative 3. So when you multiply a positive times 2 negative, you're going to get a positive, which means the function is increasing in that interval. Between negative 3 and negative 1, a number like negative 2. So again, our first factor is positive 3. When x is negative 2, the second factor will be positive 1. And when x is negative 2, the third factor will be negative 1. 2 positive times a negative is a negative, which means that the function is decreasing in that interval. A number greater than negative 1, a number like 0, all 3 factors are positive, so the function is increasing in that interval. You cannot assume that if you find whether the first interval is increasing or decreasing, you cannot assume that the other ones will just go between the two. Like if the first one's increasing, you can't assume that the next one will always be decreasing. You might remember from 30-1 that sometimes you have points of inflection, right? Where the graph actually doesn't change direction. It continues negative or continues positive after that point of inflection. So you can't always assume that they'll always switch back and forth. Doesn't always happen. But in this case it does. So we can say that the function is increasing from negative infinity to negative 3, and then from negative 1 to positive infinity. It's decreasing only between negative 3 and negative 1. Okay? So this next one is a 4th degree polynomial. We want to know where this is increasing, where it's decreasing. Again, it starts by finding the derivative, which be 4x cubed minus 12x squared minus 16x. So in this case, we can take out a common factor of 4x, which is nice because we're going to be left with a quadratic that we can factor. And the factors would be x take away 4, x plus 1. So our x-intercepts, our zeros are at 0, positive 4, and negative 1. So in this case, we're going to have 4 intervals to look at. Starting with a number to the left of negative 1, like negative 2. So again, I will use the factored form. When x is negative 2, that first factor will be negative, the second factor will be negative, and the third factor will be negative. 3 negatives multiplied together gives you a negative, which means that the function is decreasing in this interval. The next interval, we have to use a number between negative 1 and 0. So let's use negative 1/2. The first factor of 4x, when x is negative 1/2, will be negative. Negative 1/2 take away 4 is negative, but negative 1/2 plus 1 is a positive. 2 negatives times a positive is a positive. The function is increasing in that interval. Between 0 and 4, let's use positive 1. The first factor is positive, second factor is negative, third factor is positive. 2 positive times a negative is a negative, so the function is decreasing there. And after 4, a number like positive 5, all 3 factors will be positive, so the function is increasing there. So in this case here, the function is increasing from negative 1 to 0, and then from 4 to positive infinity. The function is decreasing from negative infinity to negative 1, and then from 0 to 4. So now let's look at some different functions. Instead of polynomial functions, this next one is a rational function. We want to know where is it increasing, where it is decreasing. The derivative tells us that, so that's where we start. And in this case, we have to use the quotient law to differentiate, which is the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. So that's going to give us x minus 1 minus x minus 2 all over x minus 1 all squared. So the x's are going to cancel. Negative 1 take away 2 is negative 3 over x minus 1 all squared. Remember then we let the derivative equal 0, and we found what we'd call our critical numbers from that. The issue with this one is that a rational function only equals 0 when the top equals 0, and the top is a constant. Okay? So we can't find the 0 of the derivative. It doesn't exist. But instead of finding the 0, remember that this graph also has non-permissive values. This graph has a non-permissive value of positive 1. Because you have a factor of x minus 1 on the bottom when x equals 1, you'll get a denominator of 0. Can't have that. So instead of our critical number being the 0, instead in this case it'll be the non-permissive value, okay, which is, again, negative 1. So we'll say we have a non-permissive value at, sorry, I said negative 1, it's positive 1. And that's going to give us our number on the number line to set up our intervals. Now in this case here, if you look again at the derivative, the top is a constant, negative 3. The top is always negative, and the bottom will always be positive, because whatever you put in for x, you're going to subtract 1, which might give you a negative value, but you're going to square it after that. So no matter what x is on the bottom, you're always going to get a positive value. So again, this means that you're going to have a negative over a positive no matter what x value you choose, which means in this case, the function is always decreasing, but not at positive 1, because positive 1 is where you'll have a vertical asymptote. That is your non-permissive value. So this graph is decreasing from negative infinity to positive 1, and then from positive 1 to positive infinity. So you just can't say it's always decreasing, because that's not true. At positive 1, you have a vertical asymptote there. The function doesn't exist there, so it can't be increasing or decreasing. So again, we're seeing that in some cases, your critical number is not a zero of the function. In this case, it was a vertical asymptote. Question 5, we have to differentiate. In this case here, we would start by writing it as a power, and then we use the chain rule. So dy by dx. Chain law says you're going to use the power law first, and then the second part is multiplying by the derivative of what's inside the bracket. So half of 2 is 1x, or just x on top, and then you're going to get x squared minus 4 to the positive a half on the bottom, or the root of x squared minus 4. So in this case, we do have a critical number, because the top is x. The critical number, remember, occurs when x equals 0. In this case, that will be when x is 0. Or I shouldn't say, the critical number occurs when the derivative equals 0, and the derivative is a rational function. A rational function equals 0 when the top equals 0, which is where x equals 0. But there's something else we have to look at in this case, and that is that we have restrictions on x squared minus 4, because you're taking the square root of x squared minus 4. So x squared minus 4 has to be greater than 0. So we talked about this before when we talked about the domain of functions. So this is a quadratic that opens upwards. It's the graph of y equals x squared shifted down 4 units. And if you set x squared minus 4 equal 0 to find out where the x-intercepts are, they are at plus and minus 2. So this quadratic opens upwards. The x-intercepts are at plus and minus 2. It goes down to negative 4 on the y-axis. But again, we want to know where this is positive. Where is that function greater than 0? And so now we can see that we're only going to be looking from negative infinity to negative 2, and then from positive 2 to positive infinity. So when we set up our number line here, again, we're not going to use any values in there. We can't use that critical number of x equals 0 because of what the denominator is. So we're only looking between negative infinity and negative 2. So if we use a number there like negative 3, for example, so the top number will be negative. When x is negative 3, the bottom will be positive. Negative 3 all squared is 9. Take away 4 is positive 5. The root of positive 5 is a positive decimal. But it's a negative divided by a positive, which is a negative, so the function is decreasing there. After positive 2, a number like 3, it'll be a positive over a positive. So the function is increasing there. So we would say it's decreasing from negative infinity to negative 2. It's increasing from positive 2 to positive infinity. So again, in this case, we found 0 as a critical number at first, but then when we applied the restrictions on the domain, we couldn't use 0 because that gives us an undefined value in the denominator. Okay? You can do those questions. Page 171, number 4. Yep. What kind of question are you talking about?